In this session, we talk of the power and energy consumption in DC circuits. We very well know when the current or the charge moves from one point to other, the energy is consumed. Actually, the electrons which are making collision with the other sideways electrons as well as the crystal lattice, so these collisions produce energy, and that is the basic of this energy. That's why the conductor gets heated up. So we can even term as the heat energy in this. So we'll try to find out the value of this. Remember, the value of the current for energy consumed in any resistor R, we very well know from our electrostatics that W is equal to QV. Voltage is I into T, current into time. So work is ITV, and the power is given as W upon T, which is VIT, which is V into I. So voltage into current, that means the volts into amperes gives you the power, which is in watts. Now for different type of circuits, we can plan it as I square R or V square upon R. In one case we have converted V is equal to IR. In other case we have converted I is equal to V by R as per Ohm's law. Now, one thing you must understand, that power is proportional to R as per the first thing, power P is equal to I square R, when only I is constant. That's why P is proportional to R. And whenever voltage is constant, that means the circuit is in parallel, then P is proportional to 1 upon R. So E is energy, which is I square RT, or E is equal to V square T upon R. Remember, in our household circuits, we use always power in parallel because every device comes for 220 volt. Hence, in our household circuits, remember, the higher the resistance, the lower is the power. The lower is the resistance, high is the power. It's a common question that amongst 100 watt and 40 watt bulb, which has got more resistance. So, you should understand that 100 watt will be having a lesser resistance, 40 watt will be having a higher resistance because of the P is equal to V square upon R formula. If you ever see a bulb, it is given a voltage as well as wattage. They never specify the current. So it is based on V square upon R principles. There are two circuits which you can see. In the series circuit, the power in 1 is to power in 2 will be R1 is to R2 because series circuit consumes same power. However, whenever the circuit is in parallel, you can see the power will be reciprocal of the resistances. So this is about the power in the circuits. Now we talk of another thing, which is the terminal potential, EMF and internal resistance. Remember, what do we mean by these things? Every battery is having some internal resistance, and it is due to the material of the battery, an unremovable feature of the battery. What happens? The positive charge, conventionally what we state, otherwise electron is moving, but we say if the positive charge current is moving from the positive terminal of the battery going towards the negative terminal of the battery via resistance. So in this diagram you can see from A, the charge is going, passing from capital R, is going to B. Now, should we say that the B will be always getting more and more positive and A will be removing positive? No. Actually what happens is that the positive charge which reaches at the B point within the cell moves again back to E because to complete the circuit. Circuit is completed when a charge moves from the positive of the battery, moves from via external resistance to the point B, which is the negative of the battery, and then goes back to E. So the resistance offered by the electrolyte, you can say, is the internal resistance of the battery, which is inevitable. We normally show it as small resistance. Usually we put it in the box like we have put over here, or you can just write small r, which is the internal resistance of the battery. It's a system resistance which has to be there. However, it should not be there, but practically, however small, it is always there. So under practical conditions, we can say the resistance should be as low as possible. Now let's talk on the mathematics part of it. Since small r and capital R in series, we can say the total current is provided by the EMF. So I is equal to E upon R plus R. We cross multiply. IR plus IR is equal to E. Supposing we connect a voltmeter across AB. Now AB, in the upper part of the journey, AB is from the cell, and the lower part of the journey, AB is via the external resistance R. When the current I is flowing, the I into capital R will be the voltage reading. That's why we write V is equal to IR, and substituting the value, we get V plus IR is equal to E. Remember, here V is the potential difference. Now, the cell should have the power to give the energy for the electron to move through the external resistance as well as internal. Here E is termed as EMF of the cell. V is the terminal potential difference. Remember, V is also equal to E minus IR if you substitute. So remember, there are two things. The cell's EMF is the cell's power, and the voltage across resistance IR is the voltage which is the used in useful work. I into small r, or the energy used in the internal resistance, is a wasteful work. E is termed as EMF, V is the terminal potential difference. Now you can say, whenever the circuit is having certain current, E will be always greater than E. That means when cell is giving current, I is positive, E is more than V. But what if I does not flow, or the current does not move? In that case, V will be equal to E. However, this is practically voltmeter would not give any reading because no current taken by the voltmeter. But ideally, V will be equal to E. So this situation in technical terms is called open circuit. So we say open circuit, the terminal potential difference is equal to the EMF of the cell. And there's a third case when cell is being charged. Remember, for a chargeable cell, the positive of the cell does not give out charge, it takes the positive charge. That means the current flows into the positive terminal. When cell gets discharged, the current comes out of the positive. But here the current is going into the positive. Hence we say I is negative. So when cell is being charged, I is negative. Hence the voltage is more than E. This is about the terminal potential and EMF. Now we talk of Kirchhoff's law. Kirchhoff gave laws for the multiple circuits. It has got two laws, and they are useful whenever the circuit is neither in purely parallel or series. If I cannot break a circuit in series and parallel, Kirchhoff law is always applicable. Remember, there are certain questions which can be solved by Kirchhoff's law as well as without Kirchhoff's law, but there are certain which are useful for Kirchhoff law only. Normally we cannot solve them. Let's talk about the laws. The first law, which is called the current law. The current law is based on the conservation of charge. The basis of this point is that the charge can neither be created nor be produced. So what this says is, Kirchhoff's law states that the algebraic sum of the current meeting any junction in a circuit is zero, and this is according to conservation of charge. What happens in any circuit? Let's see a circuit over here. O is the point at which the 5 wires are meeting. So let's presume I1, I2, I3, I4, I5, all 5 currents are coming. The problem now is all the 5 currents cannot reach. So some currents have to come, some have to go. So in this case, we have presumed I2 and I3 are these currents which are going out. So I1, I5, I4 are the current coming in. I2, I3 are the current going out. That means the rate of charge coming from I1, I5, I4 must be equal to rate of charge via I2 and I3. That's what we do mathematically over here. Then I1 plus minus I2 plus minus I3 plus I4 plus I5 equal to 0. When the current is coming, we are taking as a positive. When the current is going, we are taking as a negative. So, in other words, the incoming current should be equal to outgoing. The reason is very, very simple, that the O point neither can consume charge nor can deliver more charge. Now let's talk of the second law, which is the voltage law, which talks of the energy. Energy is P is equal to I square RT or VIT. So here we are using the word VI wala more important. Let's see. Kirchhoff voltage law states the algebraic sum of product of resistance and current. That is the voltage V is equal to IR. In each part of any closed circuit is equal to the algebraic sum of the EMF in that closed circuit. This is a consequence of conservation of energy. Now remember first thing, Kirchhoff's first law is based on the junction. Junction means more than two wires reaching. Second law is in a closed loop, also called the loop law, voltage law. This has to be used only in a closed loop. Let's take an example. Supposing this is the example which is coming on the screen. We have got 3 batteries in this and 6 resistances. Now we have to find the currents. Now you can see all these R1 and R2 might be in series, but no other circuit can be termed as in series or parallel. R5, R4 not in parallel, neither in series. Similarly R6, R5 neither in series nor in parallel. So how to solve this? So we first of all we presume a particular type of current and we take a junction law. Now let's say at the point B, there is a junction. I1 is coming, I2 and I3 are the going current which I have taken. The first thing is by the junction law is I1 is equal to I2 plus I3. We can reprove this thing at E, because at E I2 is coming, I3 is coming, and again I1 is going through R6. There's a common misconception that the cell also is giving the current. No, that is not the case. The cell's current has already been taken into I. Some people feel that the I2 incoming from the B part to the E part, there will be difference because of some current by the E2, but that is not the correct. All the currents given by E2 is already taken into consideration. Now when we talk of the loop, we have got 2 loops over here, A, B, E, F, A or B, C, D, E, B. Remember in the voltage law we take a closed loop. Closed loop means we'll start from the point and we'll reach back to that point. And what is the logic? When we move in a loop, I'm giving you a simple convention. There are various conventions. So by one of the convention is when you take a loop, if you move along the current, make it plus IR. If you move against current, make it minus IR. So first case, take all the I and R's, then write is equal to sign, and then we see, then we talk of the loop, not of the current, talk of the loop. If you are entering a positive of the battery, it will be negative. If you are outside the battery, it will be positive. So this is you have to see into consideration. So what do we do now? You can see, let's talk of a particular thing. We make a law, FABEF, which is I1 R1, because I go from F to A, current is going I1 and R1, then from A to B, the current is again same I1 and the rest is R2, then I move to B to E, again I am going with the current, that is I2 R3, then again I am going with the current I1 R6, then I write is equal to sign. Now for the battery you can see, if I start from F, I am entering negative of the battery and coming out of the positive battery. So positive of the battery gives current, so hence the E1 will be positive. But when we make this loop, you can say from B to E2, when we move, you are entering the positive of the battery. Hence you are going against potential. So you are at minus E2. So this is what we write about it. Similarly, let's talk of the other loop, which is ACDEB. BCDEB. Now in BCDEB also you can say B to C, I am going current I3R4 plus I3R5, but when I go from E to B in a loop, the current is coming from B to E, hence I take minus I2R3. So that's the first thing. Whenever you are against the current, make it minus. Then after this, when it comes out, E2, you have to write about battery, right, is equal to sign. Now for this whole BCDEB you can say, in both the cases from C to D you are entering a negative, coming out of positive. So it's a usual procedure, so there E3 will be positive. Similarly, when you go from E to B, you are entering the negative and coming out of positive. So it will be E2 plus E3. So similarly, this way you can use all the convention, sign convention for this, and by Kirchhoff's law we can use various type of questions. We'll discuss about them in the next slide. Thank you.